esteemed guests, distinguished speakers, and experts from Indian automotive industry, ladies and gentlemen, a very good morning to all of you. I, Divyani, on behalf of International Center for Automotive Technology, welcome you all to this awareness program on fire alarm system and fire protection system. I assure you all that today we will be gaining a lot of information about the importance and latest technologies regarding fire alarm system and fire protection system by the industry experts themselves. Now, starting with today's webinar, I would like to request Ms. Pamela Tikku, Officiating Director ICAT, to deliver the welcome address.
Thank you, Devyani. Can you hear me?
Yes, ma'am.
Okay. A very good morning to all of you. On behalf of ICAT, I would like to welcome Shri Satyaprakash Dobalji, Scientist FCFEC DRDO, and Shri Brian Klein, Thunderhead Engineering. Friends from automotive industry, colleagues from ICAT, once again, welcome to all of you on this webinar on awareness on fire alarm systems. As you are aware that CMVR has mandated fire detection and suppression system as per AIS 135/2016 for engine compartment of buses and has already notified implementation. In this context, I would like to inform you that since January 22, MORTH has issued notifications for amendment AIS 135/2016, according to which the testing of FAS and FDS in passenger compartment of buses will be mandatory from January 23. Provisions regarding protection of occupants from fire under this amendment are aimed at providing additional evacuation time for occupants and thus will further enhance the safety in fire incidents of buses through FPS and FAS. Majority of fatal and non-fatal injuries of passengers in bus fire accidents on Indian roads are due to excessive heat or smoke in the passenger compartment, which emerges due to fire in a vehicle which originates from locations other than the passenger compartment also sometimes. There was a study in 2019 which brought out the data that approximately 257 cases of accidental fires in vehicles have been reported in 2019, and out of these around 63 cases were for the passenger vehicles, buses and taxis, and around 136 for private vehicles and road carriers, and 58 vehicles for good carriers. And this data is something which is not going to reduce. It has increased because the population of vehicles on road is increased and usage is also increased. Considering the significance of the subject on fire safety for automotive application, ICAT has taken this initiative to organize this webinar for imparting awareness for fire safety as well as new regulatory requirements. This seminar also aims to bring together professionals from all segments, such as policymakers, enforcement agencies, bus manufacturers, bus bodybuilders, researchers, FDSS, FAS, and FPS manufacturers, etc. And they will be sharing their knowledge and experiences among you today. In line with the GSR number 48, issued on 27 January 22, implementation of amendment number 1 of AIS 135, ICAT Component Lab, which is testing the FDSS and FPS systems, has developed facilities which include functional test rig for FAS and FPS with configurable mock-up of complete buses, hydrostatic test rig for pipe network testing. Apart from the above facilities, ICAT has also all the required facilities which include environmental chambers, vibration facilities for component level testing of FAS and FPS systems. This webinar will focus on regulatory requirement pertaining to FAS, FPS, and also the importance of CAE in the field of simulation of fire systems using PyroSim software, fire dynamics and test facilities, which are related to FDSS, FAS and FDS. I'm glad to share with you that under Atmanirbhar Bharat campaign of Honorable Prime Minister, Ministry of Heavy Industry has assigned ICAT a task of creating technology portal for facilitating Indian automotive industry to become self-reliant by promoting innovation and adopting global technologies. Under this program, ICAT has launched a portal called Aspire, e-portal called Aspire, and through which we want to bring in all stakeholders under one platform, which includes industry, academia, students. I would like to wish this webinar a great success and hope that all the participants will be benefited by the experience and knowledge which will be shared by eminent speakers today during the technical sessions. I would like to appreciate the effort of ICAT team under the able guidance and leadership of Amit Karwal for organizing, taking this initiative and organizing this event. I wish you all a very nice day. Thank you so much.
Thank you so much for your enlightening words, ma'am. We will now move on to today's technical session. We will have 3 presentations in this technical session, starting with the regulatory requirements pertaining to FAS FDS, presenting by Sri Satya Prakash Dobal, followed by second presentation on fire simulation analysis techniques using FDS and ProSim software, which will be delivered by Mr. Brian Klein, and thereafter an overview of FAS, FDS, FDSS test facilities of ICAT and other CTL test facilities, which will be presented by Mr. Amol Kumar. Moving on to our first technical presentation of the day, I would like to invite Sri Satya Prakash Dobal, Scientist CFEE-SDRDO. Sri Satya Prakash Dobal is a postgraduate in chemical engineering with diverse experience, cumulatively more than 30 years in chemical engineering research, project management, and human resource management from his past association with International Organization OPCW, a private sector manufacturing plant, and a public funded R&D organization DRD. He is currently working as Scientist F at Center for Fire, Explosive and Environment Safety CFEE-SDRDO Delhi. He is currently working in the research areas related to fire and explosive safety, fire chemistry, safe and secure management of hazardous chemicals. He has 1 patent and more than 30 publications to his credit. We are privileged to have you, sir, as our first speaker today. You are now requested to start with your presentation.
Thank you very much for the introduction. Can somebody confirm whether the screen is visible?
Yes, the screen is visible and you're audible as well.
Okay, thank you. So let me just first thank ICAT for giving this opportunity to present on fire alarm system and fire protection system, a new initiative by the Ministry of Road Transport and Highways. And our association, the DRDO's association with this activity commenced in 2020, mid of Corona period, precisely in June 2020, when we were approached to work on this issue. And the trigger for working for concern from the Ministry of Road Transport and Highways had been the incidents on roads and highways involving a large number of passengers. So I'll go through in my presentation about talking about the background, why we did what we did, and how we formulated the design aspects, how we finalized our objective, and then design aspects, and followed by the various experiments which have been carried out at CFEs. I am right now engaged in another activity, so I'll be presenting in the next 30 minutes to the large extent whatever I have to communicate, and in case there are further queries, I'll be happy to respond to them subsequently. So if you look at why we are here today, is because of this notification, which came in on 27th of January 2022. It is the Gazette notification, and this is the amendment in CMVR rules 2020. These are known as the CMVR amendment rules 2022. If you going to the, yeah, so if you read the Gazette notification, it says that if you look at paragraph 2A, it is talking about the implementation of AIS 135 in type 3 buses. Similarly, the amendment in the rule in 2B with respect to AIS 063, which is basically the school buses. And the table makes it amply clear that fire alarm and fire protection system in occupant compartment, type 3 buses of category M3 and school buses. The standard which is applicable is the AIS 135, and the time period given is 12 months, which will be ending in January 2023. So we expect implementation in January 23. That is the current position. How we come to this position and what have been the various aspects which we studied. In this slide I'll give you a little glimpse of the Detector. ICAT talked about 2018, and we had 155 deaths of 175 passenger vehicles incidents, and this was a high number. Although these numbers vary from year to year, but this definitely presents a challenge to the fire safety community and the transport ministry as such. And if you look at the likely causes, these are the heat, vibration, defective maintenance, collision, compromises on the design, and there have been many aspects which lead to these incidents. So there is, on one way, we should be dealing with removing those aspects which impact the buses in their operation. At the same time, incorporate new measures so that the risk and the hazard is managed. If you look at the fire in the buses, because primarily in my presentation I'll be concentrating on buses, and whenever I say occupant compartment, you can also consider as a passenger compartment, because these two terms have been interchangeably used in my presentation. Although in the standard the term has been used as occupant compartment, so that's how you can understand it. So looking at the fire in buses, the most culprit is engine compartment, where there is a fuel, there is a heat. So if you look at the fire triangle, all the elements are present there. So as soon as it reaches to a threshold, there is a fire in the engine. There is a possibility of a fire, and most of the fire originates from there and then propagate to other areas of the bus. If you look at the research which has been carried out worldwide, the smoke and the fire effluents reach to passenger compartment within few minutes, and the maximum window of 4 to 5 minutes is available for any action if the engine compartment fire suppression is not available. So looking at I'll talk about engine compartment fire a little bit in subsequent slide. If you look at bus passenger fire compartment fire risk, so when the problem was given to us, we had to give a fire protection system for occupant compartment. But if you look at the origination of the fire, or the origin of the fire, is always or most of the time is outside the occupant compartment. So in that case, our effort, even if we concentrate on passenger compartment, is not enough. So we have to deal with in a holistic manner, so that we deal with the fire which is generated externally. So in that spirit, you look at the implementation of FAS and FPS is one step towards a higher safety, but it is not the ultimate step in my view. So the passenger compartment gets affected when there is an fire breach from engine compartment, or there is a short circuit in the driver cabin, or in the passenger compartment, or if there are external fire due to leaking fuel lines, or braking system, or tires, then that also may reach to passenger compartment. So this is the typical fire scenario for a bus compartment. If you look at the right hand column, fire with or without involvement of collision may originate in the engine. The fire may be due to fuel spill, it may be because of the collision, or maybe otherwise. Fire originating in passenger compartment, which is generally very rare, but it could be because of electrical short circuiting. And then there are deliberate fires in the compartment, and then there are fire in other unknown areas. And these could be the fire categories which uh, we are aware of when we are talking about a solution for fire protection system. So when we look at what kind of a fuel is there, so we have a variety of fuel present in the passenger compartment in the form of fiber boards. There are floor boards as well, then foam, rexine, fabric, wood, and plastic. There are electrical insulation material. So all class A combustible most of the time, which is there in the passenger compartment. And the other type of fuel, for example, hydrocarbon fuel, which is type B, and there could be other, like in today's scenario, even we have battery fire, then there is a different kind of fuel available in the bus. If you look at when we looked at this problem, and we referred NFPA 556. NFPA is the US standards on fire safety, and this is the one which is relevant to the problem in hand. So we have challenges with regard to detection in the engine compartment, but once it is detected, the suppression is not that difficult. In the passenger compartment, the suppression is difficult because if the fire is originating outside, then the suppression is not achievable within the given available time. Then the trunk or load carrying area, again the detection, because of congestion level, the detection is an issue. Pool fires from fuel tank failure, that is another area where detection is a challenge. And then there are external heat sources. So these are the challenges which still we will be working on, and we will be looking at some solutions which can be used in these areas, which we pick up from the industry and apply in the scenario in the bus. Okay, so if you look at closely, until 2020, when we started working on this problem, the school buses were already slated to introduce FDSS and FDAS. FDAS from April 19 and 1st April 19, and FDSS from 1st April 20. And these two FDAS and FDSS were there as part of AIS 135, and which only covered engine compartment. So the majority of the fire originating in the bus was tackled through FDAS and FDSS, and this was implemented in school buses primarily. If you look at the international references, the similar guidance you can find in UNECE Regulation 107, which also talks about for the engine fire. And the guide which also talked about, which we referred for most of our referencing purposes, guide on methods for evaluating fire hazard to occupants of passenger road vehicles, is NFPA 556. So I would encourage the participants, those who are interested, to look at it and go for more holistic solutions in bus fire. Okay, so just to tell those who have not been very conversant with fire risk management, so there is a passive approach and then there is an active approach. So passive approach, we already have a lot of elements in place. There is a firewall between engine and passenger compartment. Then there are restrictions or regulations with regard to the materials which you used, so with regard to flame retardancy. And then there is a possibility of using fire blankets in case of so these are all passive approach which becomes part of the complete solution. So if you look at the progression, the passive approach comes first, and then the detection, and then followed by suppression. So in that sequence, we have still a lot of work to do on addressing the fire risk in buses using passive approach. So there, in my understanding, there is still a lot of scope for studies on materials, the choice of materials we pick up for passenger compartment and other fire sensitive areas in a bus. Then we have the second line of defense could be our detection system. So the more robust our detection system, and many a times we should always be aware that the passenger compartment is a manned area. So all our efforts should be in incorporating that element into mind. Then the fire suppression, primarily in bus compartment fire, suppression is not achievable if the origin is somewhere else. Suppression can happen if the origin is within the passenger compartment. So these are the two studies which we carried out, that fire originating in the compartment, and then we cannot have a fire which is not proportional to the expected risk there in the bus. So a very similar scenario was created for fire suppression within the compartment, and looking at the fire protection from a fire which is originating other than the passenger compartment. The other fire scenarios were studied using simulation in PyroSim. So I am happy to know that there is going to be a follow-up presentation on PyroSim. So definitely we will be able to know much more on that front as well. So the challenge is basically the evaluation of design alternatives to assess the sufficiency of time for escape from the fire scenario. So this was the key challenge which we faced, and we decided to work on. So design alternatives also means what kind of a different fire suppression agents, the means of delivery, the means of storage, the mechanism to disperse the fire suppression agent in the passenger compartment. So all those elements were studied, and with regard to sufficiency of time, there has been a lot of debate what time would be sufficient. So the mostly debate concentrated on 3 minutes to 5 minutes. Eventually, because it has got an implication on the load carrying capacity of the bus, as well as on the what type of bus we are talking about. So 3 minutes of sufficiency for evacuation window was considered sufficient if the detection system is working in the bus. So if you look at the objective, which we, based on the various design elements, we finalized the objective: safe evacuation of passengers in case of fire by using low pressure water main system. So that is was the objective. Then we worked on this aspect further. At the experimental level, there are certain some details are given in this slide. Looking at the system parameters. So, for example, what should be the mist concentration? What should be the orientation? What should be the fire size? So, more than 50 experiments were carried out. The pre-burn time 60 seconds was given in this experiments, and the temperatures which we have achieved in the experiments were recorded using thermocouple, and heat flux sensors were also used to measure the heat flux. And all these two elements or parameters were compared with the simulation using PyroSim. So then, subsequent to the passenger compartment fire, we also studied additional external fires from the fuel tank as well as from the braking system. And the system was evaluated and compared, and we found that the system is effective in blocking the entry of the fire effluents or smoke and hot gases into passenger compartment. That is one. And the second thing is it immediately lowers the temperature in the passenger compartment, providing a window to the passengers. So it is still effective, although it's not able to suppress the fire if it is externally originated, but at the same time able to provide the window and meeting the objective of the system. The evacuation time studies were carried out using Pathfinder. since these studies were not carried out with all variety of buses, there had been the choice of the bus has been a 52-seater standard bus, and the bus has been used. I will show you some pictures in the subsequent slide, where the Pathfinder was used for different scenarios. If the fire location is different, if the mix of population or mix of passengers are diverse, so there are elderly, there are children, so we could find that the evacuation time window of 3 minutes is sufficient for achieving the objective of the system. Design fire was primarily a combination of, it's a replication of the seat material which is there in the standard bus, so foam, fiberboard, and the cotton fabric, and ignition source was 20 ml N-heptane and 40 ml LDO. So this was to initiate the fire, and a pre-burn time was given so that the fire the foam is in the fire, and then we have the more reasonable outcome of the experiments. This is a quick look at the typical piping and test instrumentation. So this is a 52-seater bus, and if you could see on the right side, then there are heat flux sensors which are red in color, and then there are thermocouples which are placed at different locations. There is a side view and there is a top view, and then there is a picture of the bus which is where the fire is being created in the middle of the passageway. But there had been other studies when the fire was created on the seats, on top of the seats. So there had been different places where the fire was created, and on the left side there is a picture of the bus which was used in these experiments. So the same bus was also through a 3D design was mapped to a pyrosim, and where this setup was created. The length, width, and height is of a standard bus. The seating material involved combustible, polymeric mass, and cellulosic mass. And you can get an idea that the typical the weight of the polymeric combustible is about 40 to 50 kg. Weight of cellulosic combustible is 5 to 10 kg, and exposed surface area of combustible was 10 meters square. So that is, and there were 3 scenarios of probable fire types which were generated in this: passenger compartment fire, engine compartment fire, and external fire, tire fire, and oil tank fire. So these scenarios were created to understand the impact of fire and then impact of mist on the fire. So how the smoke layer is getting cooled, how the overall temperature in the compartment is rising over a period of time. So these studies were carried out to come to an understanding that there could be a system that can be used for meeting the objective which we initially set, that is providing an evacuation window in case of a fire, irrespective of the origin of the fire. So that is the brief background. I'll now quickly move on to the EIS 135 amendment. So now, once we carried out all the experiments, there had been engagement with the stakeholders from the regulators, the OEMs, the fire safety professionals, and I'm thankful to them to come on board for that was in 2021. For 6 to 7 months, we were constantly working on this aspect and finalized the other parts. So AIS 135 was upgraded, or basically additional parts were added to it to cover the passenger compartment, which the standard says occupant compartment. So part 1 and part 2, which were dealing with the engine compartment, part 3 and part 4 have been introduced to talk about fire alarm system, part 3, and fire protection system, part 4. So I'll quickly go through some of the provisions and some of the test requirements from the standard. Since the standard is voluminous, so I will not be able to completely justify my presentation with respect to the amendment. So I would encourage you to look at the amendment itself and go through it. And if you have any queries, then we can discuss it further. So you can understand that the amendment was with respect to incorporation of occupant compartment fires. So enhanced scope now includes requirements of fire alarm system for bus occupant compartment, and then there are annexes related to FAS approval. So these are 1A, 3A, 4A, and 6A. Then we have type part 4, which is approval of requirement of bus occupant fire protection system, and then annexes related to FPS approval, 2A, 3A, 5A, and 7A. So these are the various different annexes, and then appendices, testing details, talking about the test apparatus, the protocol, and then general guidelines which are there in the. So this is a list of summary of annexes and appendices. So there are 3 different colors. So first 3 talks about information for type approval. Then the next 4 talks about the various requirements. For example, requirement as a component or requirement as a installation in a specific occupant compartment. Then we have guidelines for deciding whether testing is needed. Then test apparatus, test fires, general test specification for OC, and general guidelines. So this is a summary of the amendment which is there in AIS 135. So the emphasis on AIS 135 is potential fire hazard. So there is a fire risk assessment which needs to be carried out. You will agree with me that buses comes in various different shapes and sizes, and they also come with different materials which are there inside the occupant compartment. So it is important that we carry out any activity of installation based on the risk assessment, and some indication of risk assessment is given in the standard, and the basis for which installation of fire alarm system and fire protection system should be based on the fire risk assessment within the occupant compartment to make it effective. So one clause it talks about within the occupant compartment the potential fire hazards to be identified, and the fire detectors shall be positioned appropriately to cover the fire hazard. So if you look at the fire detectors, we have choice of fire detectors. So we in our study used smoke detectors, but when we discussed with the other stakeholders, although in our study we used heat detectors, we used linear thermal detectors, but we realized that the trigger time for all these detectors other than the smoke detector was very high. So although the technology is very simple, but at the same time it is prone to a lot of false alarms. So this element of false alarms can be balanced if the driver and the co-driver on board is aware about the possibility of a fire alarm and nullifies that element of false alarm by inspecting the area where the alarm is originating. So so simplistic solution would be starting with the fire alarm with the dust protection measure, but at the same time there are more elaborate possibilities, for example CO sensor or UV sensor. So this particular standard does not talk about what kind of detector you should use, rather it just talks about that there should be a 30-second which I'll talk about in the next slide. 30-second it should give an alarm, and so that is the time limit which is given. So it's a performance based element which has been incorporated, and then in case of a detection there should be an audio visual alarm of 90 dB, and this can be integrated with the current FDSS or FDAS. There can be there is in the standard there is a very interesting provision that additional heat sensors to monitor temperature near fuel tank. It could be a plate thermocouple, or it could be a linear heat detector, so can be installed near a fuel tank or near wheel braking system, so that we have an early detection of rise in temperature and there is an enhanced fire safety. So many a times if the fire remains undetected and is away from the passenger compartment, then it becomes large enough to be noticed by either by the passerbys or by the occupants. So to eliminate that possibility and to get the detection as early as possible, these provisions are possible, but this is not a mandatory requirement. These are additional requirements which are suggested to increase the fire safety in the bus. So if you look at annexes as components, the fire shall be detected and warning signal shall be acted within 30 seconds after ignition of the test fire 8. So test fire 8 is very similar to the fire which we have used in our experiments, which involved the fiber board, the foam, and the cotton wrap with the LDO and hapten. So same fire has been described, and the effort of the team which were involved in the standard making was to make it in such a way that it cohesively gels with the FDSS and FDAS provisions. So similarly, the fire number 7 is up to is for the engine compartment, and fire number 8 onwards up to fire number 11 is for FAS and FPS. So FAS is for fire number 8, and if we are talking about installation, so that is the detection which should be within 30 seconds, and if it's an installation, then there are zones which have been suggested, zones of 3 meter each, and each zone of 3 meter along the length to cover to have at least 2 detectors on the ceiling farthest from each other. These requirements are from the perspective of smoke detector, but these can be altered if there are different kind of detectors are being used. The time for activation remains same, 30 seconds, and the test to be repeated at each zone boundary to cover at least 2 of the following fire locations farthest from the passenger exit. So near driver seat, in the middle of the passenger compartment, or rear of the passenger compartment. So these scenarios are to cover the maximum coverage of detectors. The test is considered passed if success was achieved in the first attempt, or at least two of three attempts. So if the first attempt is failed, then if next 2 attempts are passed, then the test is considered passed. So this is the provision for fire alarm system. If you look at the part 4, as I told you earlier, that based on the evaluation of efficacy of water mist system in occupant compartment of standard size bus, in case of seat fire, these studies were carried out through experiments, and in case of external fire, through simulation studies, which led to cooling and scavenging of gases and enhanced evacuation window. So the part 4, this is the basis on which the part 4 was formulated, and the provisions are made in such a way that the design details are already incorporated in the standard. So to large extent, the effort is not required to carry out a lot of calculations or so there are engineering aspects which needs to be tackled into. So if you look at it also starts with the documentation of fire risk in the occupant compartment. So there can be a single fire risk assessment study of a bus, which based on which the alarm system as well as the fire protection system can be configured, and enough flexibility is there in the standard to incorporate these aspects. So if you look at the documentation, it must cater for the total quantity of class A fire source which is there and how it is spread out in the compartment. If it is studied carefully along with the heat source, then there is a higher probability that we will be able to achieve the objective of the evacuation. The identification of surfaces where temperature may reach above 80 degrees. So in a normal operation, if there is no fire protection system there, then the temperatures near the engine due to auto ignition of various gases can reach more than 80 degrees, or they can be the gases or substances which are in contact with the surfaces. So the barrier which I was talking about between the engine and the occupant compartment, or there could be the junction boxes, or where there are a lot of electrical electrical connections are there or electrical joints are there, and there is a high voltage and high current in any particular area or in any particular junction, or there could be hoses and containers with flammable liquids maybe beneath the bus, or there could be a possibility of pressurized gas. So all these pose a fire source, and then if the combustible material is placed nearby, then the fire is expected to in case of an accident or in case of initiation, it is likely to extend to the combustible area which is adjacent. So the purpose of this clause 4.5.2 is to detail this aspect of fire risk assessment, so that we can have a location and orientation of nozzle, and we understand that this particular standard is for standard fire load and cannot be used for elaborate partitioning or decorative elements which are there in the buses. Sometimes we find that. If you look at design, which is clause which is 4.5.5, ease of implementation and reduced ambiguity, that was the objective. And the design basis of FPS for water mist system was 0.65 liters per minute per meter cube mist injection rate. So this is the total aggregate mist injection rate from all the nozzles. And the seating capacity has been used as an indication of standard fire load. So when we were formulating this standard, there was a discussion that can we use it for all buses? So we realized that there is a definite fire load beyond which this will not be very effective and may not be of use. So there has to be further studies on those cases. So a standard fire load, so then there is a seating capacity versus a volume. So there may be coaches when there are less number of seats, but same volume. So that will not be covered in this particular standard. So table for gross volume range and number of nozzles have been this is more of a prescriptive in nature, 9 to 35 with enough flexibility. So water quantity from 55 liters to 210 liters. I'll be talking about that in subsequent slide. Then volume up to 80 meter cube was subdivided into 7 ranges, and gross volume range of the OC shall be arrived without subtracting the volume of installed component seats, etc. from it. And the design features are applicable to the standard bus of volume and seat matrix up to 80 meter cube. Buses having special comfort arrangements or some compartments and occupant area shall be subject to simulated fire test as per Appendix 6. So primarily this just gives a way out how to handle those scenarios. It suggests to go for simulated fire test, but there could be even further. There may be a need for further discussion on as the cases evolve or as we have the case in hand. So this is clause 4.5.5. Talks about seating capacity, gross volume range, the number of nozzles, and the water quantity. So if we use this table, then we will be able to achieve the requirement of 0.65 liters per minute per meter cube. That is the mist injection rate that the design basis we will be able to achieve. But if you look at this table, if we are talking about seating capacity of 30, but we are talking about seating or sleeping capacity of 30, and talking about a volume of maybe 50 meter cube, then this definitely is not applicable. This standard is not applicable. The clause 4.5.6 and 4.5.7 talks about the propellant air. So the pressure of the air at the discharge point should be enough to create 8 plus minus 1 bar with the water in the pipeline, and nozzle characteristics have been determined at 7 bar, which are these are the nozzle characteristics, and there has been enough flexibility. So with the droplet sizes as well as the cone angle and the nozzle flow rates, so that this becomes more of a performance based than the standard. So in the nozzle spacing, there is a recommendation. Then total discharge time should not be less than 3 minutes. So that again an area where I'll talk about testing, so this will be part of it. It is acceptable for water mist system to have more quantity of fire extinguishing agent and more discharge points. So again, there is a possibility of risk assessment or adjusting these elements, but it should be based on a analysis fire risk assessment of the bus and should not be blindly more or less. Otherwise, it should stick to the requirement of the standard. Installations requirement, discharge points along the length of the bus, angle downwards to provide wet coverage to window and seats located just below. So again, all these points are the guidelines for installation, and the objective is that the water mist is uniformly spread in the total compartment, and the material of construction should be SS 304 or better, because we are dealing with water, and if the water stays for long, then there could be possibility of corrosion and maybe leakages. So system reliability will be at stake. So we consider the SS 304 or better if there are better options available. So that should be explored in 3 different headers. So when we experimented, we did experiment with 2 headers and 3 headers, and we realized that the 3 header is the best configuration, primarily because of the curvature nature or nature of this roof of the bus. So there is a mid section which extends other than the side sections, and because of that there is a requirement to have a mid section to cool down the smoke layer which may get accumulated in the passenger compartment. So the 3 different headers and some spacing related details are also given, but these are up to, so these are recommendatory, not specific that we should stick to. This was depending upon the length of the bus and the geometry, the details inside the bus. We can work on this aspect along with the fire risk assessment. So always in the back of the mind, we must keep fire risk assessment as the basis on which we should do any alteration from the standard. So okay, so this also, if you go for the standard design and a standard bus with a seating capacity mentioned, then we have given in the standard the nozzles on the right side, middle section, and the left side, and the network should be installed in such a way that there is no accumulation when it is not functional, and the pipe work should be hydrostatically tested and performance documented for review of approval agency. So this is again one of the elements of the test of the system. So hydrostatic testing. So I'll quickly go through the tests which are related to FAS, fire alarm system. So fire alarm system, primarily functional test. I talked about fire size 8, mandatory documentation, which is fire risk assessment. The test for fire protection system include fire protection system functional test using water discharge rate test, hydrostatic testing, design parameter verification using checklist, mandatory documentation, which is fire risk assessment again from the perspective of FPS, and then there is a one from the perspective of fire alarm system. An optional simulation fire test 9 to 11 expected to cover cases other than being covered in clause 4.5.5. So this is the checklist which we finalized in the standard. So air quantity, what should be the criteria? Air cylinder capacity. So then what should be the test pressure? 1.5 times of the operational pressure. Then pressure reducing valve, how it should be able to reduce the pressure from the air cylinder to the desired pressure in the water tank, water cylinder. Then solenoid valve, so that it can be remotely operated from the diver's cabin, and then water cylinder capacity, pressure, test pressure, nozzle characteristics we already talked about, which included flow rate, Sauter-Mean diameter, and the D90. Then total nozzle layout, again it refers to the clause. Pipe network pressure optimization. Again, this is a very important aspect, that when we work on a piping network, we should be able to optimize the pressure in such a way that the minimum pressure of 7 bar is achievable at the nozzle, or 8 plus minus 1 bar is achievable at all points. Pipe and fitting materials and types, relevant standards. So there is an IS standard for the water mist system, and all the other relevant aspects should be picked up from there. General guidelines we talked about in the standard. Component selection. So how do we select a component so that it is reliable? Then documentation. What kind of operational documentation, maintenance documentation, FAQs we should have for the system. Maintenance requirements. different kinds of maintenance. The maintenance when system is not operated, but from time to time. So these are periodic maintenance. Then there are breakdown maintenance. So it mentions all these elements. And you must be aware that this is my last line of safety. If you look at in the passenger compartment, there is this is a manned area which I already talked about, and then there is onboard fire extinguishers, portable fire extinguishers available. So any system, if any sophisticated system will not work if the people who are operating it are aware about it. So they have the first line of defense is basically their extinguishers, where in any case of alarm they should be able to handle and suppress the fire at its earliest stage, possibly at the incipient stage, but as soon as possible. And then subsequently, if the fire goes out of hand, there is a requirement to lower down the temperature, then the system should be operated. So this definitely requires involvement of the drivers and the co-drivers at a large for making it effective. So a special emphasis, in my view, should be given on this aspect, so that this system remains functional during the lifetime of the bus, and the upkeep and maintenance is done on a timely fashion. Then recommended type testing of the components for shock, vibration, cyclic, and top test. These are recommended type, and eventually I expect the industry will be more confident that these becomes a mandatory part of the components. So since it's being implemented at this stage, this is a recommended type, and then the regulatory authorities will come out with more details on this aspect. The component level test guidelines are recommended to be as per clause 4.2 of this appendix and as per AIS 018, which also talks about automotive industry standard for component level test. Test and approval requirements of water system as per IS I talked about 15519. So this is the gist of the standard. I did not cover due to lack of time because it's an extensive standard. So I covered the salient part of the standard. And you must be aware that this is one step towards performance-based system. So I do not see that this is the end of the work in this area, and I hope and expect that the other agencies will also join in and work on this further. We did simply, and there is a need for further work on this, that we have established fire safety goals and objectives for bus, and then we analyze the fire scenarios, and then these scenarios can be more realistic if we have data from the ground. So as we were talking about earlier in the slide, for 2018 data that comes from the Crime Record Bureau, but hardly this information can hardly be used because the origin of fire and there are other details are not available. So if there is a data collection on this aspect, there can be more realistic studies and the prioritization of activities. Then quantitative assessment of design alternatives against the fire safety goals and objectives using accepted engineering tools, methodologies, and performance criteria. And engineering tools also involve the simulation tools which we have. Then we have analysis and design process will involve fire growth modeling and testing of final designs, and fire hazard control for it, fire properties of materials. So this is another area which is I would like to emphasize, which is the last point about the materials. So as of date, at least I am not aware of a comprehensive tracking of these materials and for their heat release rate, ignitability, and if there are norms, those are loosely bound. So we might like to look at this aspect more closely, so that we have our first line which is related to materials, the second line which talked about fire extinguishers, and third is the fire protection system. So in that aspect we can give higher priority to quantify, have reasonable targets for fire properties of materials. And in the conclusion, I will say that fire protection system complements fire extinguishers and passive fire protection measures. So I have been harping on or repeating this part several times, and I expect that if there's a one takeaway which you should take, it should be that fire protection system is a complementary to fire extinguishers which are already there, and the passive protection systems which you have all measures which you have already incorporated. FPS enhances evacuation window to the passenger, irrespective of where it is originating. Selection of reliable component needs to be addressed for implementation, and prioritization to bring out test protocol for FPS and FAS. So that should be more priority on, so that there is a more engagement of the industry on this element. What for the research institutions and the other organizations, what could be the way ahead? Further studies on performance-based design approaches, which I talked about in the previous slide, then industry participation for component level reliability assessment and addressing the fire safety in vehicles with different types of fuels. So we must be mindful of the fact that now there are different kinds of fuels which are being talked about, be it hydrogen, be it a mixture, liquid hydrogen, the EVs, and so there are variety of fuels which which will we be encountering in future. So how we can comprehensively deal with the fire safety, that needs to be looked into. So with these words, I'll conclude my presentation, and I thank ICAT for giving me this opportunity to share my views on this. And I must say towards the end that the standard has been the outcome of efforts of so many people, including regulatory authorities, OEMs, who have gone through this draft, and I thank all of them for their support. Thank you.
Thank you, sir, for excellent presentation. It was very precise and relevant. We will take question answer at the end of the technical session. We will now move on to the second. Yes, sir.
I have a request that since I have another engagement just after this, if there is any question, please forward it to me and I will respond it later. So I thank for the engagement of participants. Thank you.
Okay. Thank you. We will now move on to the second technical presentation of the day, which will be delivered by Mr. Amol Kumar, Deputy Manager, ICAT.
Hello, I'm audible. A very good morning to all of you and distinguished speakers and delegates. And thank you to Mr. Chauhan for giving the in-depth knowledge about the FAS and FDS standard. My presentation is moreover about the overview of the FAS and FDS facilities and other CTL facilities for bus testing. Hello, my voice is. Thank you. Currently, AIS 135 is applicable for the fires originating from the engine compartment. And in this standard, there are two types of testing, that is FDAS and FDSS, which is conducting on the mock-up of the engine compartment and fire originating from the engine compartment. However, there are incidences when we see that sources of fire is not the engine compartment. It is inside the cabin passenger due to the short circuit or some external sources. So, in order to detect or suppress this fire, there is no facility in terms of detector or protection currently. So, also there are incidences considering the fire incidences in the passenger compartment of the buses. Government of India had taken the initiative to have regulation on FAS and FPS as well. So, in this regard, Ministry of Road Transport and Highway had issued GSR number 48 on 27 January 2022 for implementation of amendment number 1 to AIS 135, which will be effective from January 2023. So, you can see that these are the incidents of bus fire. This is the recent incident in Maharashtra's Nashik, where a bus catches the fire. In this incident is recent on 8th of October. So, in this incident, a bus coming from the Yavatmal to Mumbai collided with a truck, which going to the Pune from the Nashik earlier. So, when I was preparing this PPT on Saturday, so I got this information that from the news that this bus is catches the fire in Maharashtra. So I have included this in this PPT. So main source of this fire was external in this case due to the collision of the with a truck. So in this incident, there are 12 casualties and 38 were injured in this case. So another incident was one school bus in which this school bus catches the fire in Navi Mumbai. So this is also the very critical case when the fire occurs in the school buses because this involves the small children. Therefore, it is very critical to implement this standard. So, in this incident, as many as 4 students of a school in CBD Balapur had a very narrow escape after the school bus that they were about to board at pickup point in Kharghar suddenly caught the fire. So, but it was a fortunate that all 4 students were escaped from the bus before it caught the fire. The main source of this incident was a short circuit in the front engine bonnet. So, so the main source was the engine compartment in this case also. This is the third incident. In this incident, 21 children was boarded on this bus, and this incident was of a school bus of a Delhi. So in this incident, 21 children were escaped from the bus just before the fire. So this incident was July 2022. No casualty was reported. It was a good, but this 21 children had a very narrow escape after their school bus caught fire in the incident. So in this case also, source of fire was engine compartment in this case. This is the fourth incident. This incident, above 2 incidents are for school bus, and this incident is from the passenger bus. So in this incident, bus was on its way from the Jammu, from the Katra, when it caught fire near the Karmal, located about 1.5 kilometers from the Katra. 4 pilgrims cheered to death, and 24 persons received burn injury when a Jammu-bound bus caught fire near Nomai. So this is a very unfortunate incident. In this incident, when investigations was happened, the source of fire was also from the engine compartment. So it is a very, we can see that all the incidences, source of fire was engine compartment, except one in which source of fire was collision with the truck. So on seeing all these incidents, it was good that the Ministry of Road Transport has circulated the circular notification so that bus passenger compartment is also included in the existing AIS standard. So these are the applicable test standard in India. Reference standard AIS 135 2016. This amendment number 1 is for FAS and FDS. So standard title is AIS 135 Fire Detection and Alarm System and Fire Detection and Suppression System. Applicable area. Applicable area for this is passenger compartment of buses and type 3 buses of category M3 and school buses. As we have seen, the two incidents are from the school bus and 2 from the passenger buses of long distances. So these 2 type of buses are included in this standard. And notification came as per the GSR 4080 on dated 27 January 2022. So as per this notification, this standard is applicable from January, within the commencement of this notification, or 1 year after this commencement of this notification, that is 27th January 2023. So what are the main key features of this standard? Because previously there are 2 types of testings, FDAS and FDSS. So this is equivalent to that one, but it is for the passenger compartment. Like FAS, this is the system of a fire alarm system in the passenger compartment. This system comprises of the component and subsystems required for automatically detecting the fire, heat and smoke in the occupant compartment and initiating an automatic alarm. So there are 3 types of various types of detectors, but I have mentioned 3 of them, which are also mentioned in the standard. One is heat detector, second is a smoke detector, and third one is carbon monoxide detector. So heat detector. So this is heat detector is a sensor that senses either abnormally high temperature or rate of temperature rise or both, coupled with a smoke detector. And this smoke detector is a sensor that senses the presence of significant amount of smoke as fire signature. And third one is carbon monoxide detector. Carbon monoxide detector or CO detector is a device that detects the presence of carbon monoxide gas as fire signature. So I have highlighted these 3 type of detectors, but other detectors can be used with this FAS system, like UV and any advanced detector that can be the advancement in this technology. And what is the fire protection system? This fire protection system is a low pressure system As per the standard, low pressure means their pressure should be less than 12.1 bar or less, and which comprises of the necessary elements to manually trigger release of water mist with specific characteristics capable of suppressing the designed classifier in occupant compartment, as well as controlling the temperature inside the occupant compartment. When origin of fire is not the occupant compartment, to provide at least 3 minutes of evacuation window to the occupant compartment. And what is this water mist system? A distribution system which is connected to a water cylinder as atomizing media through the suitable number of nozzles which are capable of delivering the water mist that meets the performance requirement as per this system. So in this water mist system, these small droplets generated. So this small droplet, because the small droplets generates the higher heat capacity. So it is recommended in the standard. There are certain type of nozzles. The nozzles size and dimensions are fixed. So as per that nozzle sizes, these droplets will automatically generated. So, and this is less than 1 mm of dia of these droplets. So this small droplet maximizes the heat absorption due to their comparatively large surface area. So therefore, this water mist system is so effective in this case for passenger compartment. And evaporation of smallest water drops. So this smallest water drop will absorb this heat from the passenger compartment and evaporates. So evaporation displaces this air equivalent to 1650 times its original volume. So this water mist system is so effective in this case. There are more than 6 general requirements for FAS and more than 9 for FPS in the standard, but I am highlighting few of this in this presentation, which I see the more critical point of view. For a fire alarm system, the smoke or CO detector have a dust compensation feature. So also this CO detector conform to the relevant IS or UL and FM global standard. So this we will check during the testing at the ICAT. And a minimum sound level of audio-visual alarm shall be 90 dBA. This is to make it audible to the passenger seated on the rear seat of the bus. So it should not happen that voice would not go to the last seat of the bus. So this is the minimum dB level has been defined in this standard. So we have to we will check this during the testing, this dB level. Otherwise, optionally a hooter system as approved under the AIS 52 revision 1 can be used with a minimum sound level of 90 dBA. That hooter may be common with the FDAS and FDSS, which was already approved at the time of FDAS and FDSS testing. So that can be used for FAS and FDS also. And for fire protection system, fire alarm system and the fire protection system shall be operational irrespective of whether engine is running or not and vehicle's attitude. This fire alarm system is irrespective of the engine is running or not, this should be working. They're working, we will check at the time of vehicle level evaluation. Pressure of the propellant gas shall be operated to achieve 8 bar nozzle operating pressure at all discharge points. So this pressure of propellant gas, we will see as per this whole water mist system is as per the standard working pressure. So this will depend on the as per the manufacturer. So this operating instructional pressure we will check during the FPS testing. These are the testing requirement, mandatory test as per this AIS 135. First is as per clause number 3, FAS test, fire alarm system. I will not go to in depth about this test. I will only highlighting this one because Satya sir has already described in his lecture. So I will only go through it. As per clause 4.1, evaluation test for FPS. In this test, there is a 12-point checklist. We will verify this checklist during the testing. And 4.2 clause hydrostatic testing. This we will be done. This testing will be done as per the hydrostatic test that we will develop at ICAT. And 4.3 clause functional test of FPS. In this test, we are fabricating one mock-up for bus. So within that mock-up, we will do this FPS testing, and we will check the capacity of the fire this FPS system, so that we will check 3 minutes of evacuation time. There are another guidelines standard. Guidelines testing in this standard, but these are guidelines which we will not test as a mandatory one, but this is as per the manufacturer. They can do these tests. They have to ensure these tests before the actual testing. So this is as per 4.1 functional test, 4.2 sine sweep vibration and mechanical shock test. And another is 4.3 clause as per that high temperature electronic component for electronic component test and endurance test at high temperature and mechanical component test, and low temperature test for electronic and mechanical component, and salt spray test for only electronic component and salt spray test for mechanical component also. And endurance test is therefore high humidity. Also drop test is also therefore as an optional one. So keeping in view of this standard, ICAT is ready to do this testing. Because as per in this standard, it is mentioned that these tests are done on the bus, but we are getting the queries from some of the manufacturers because cost of this bus is very high. So considering their request, ICAT management has decided that we will fabricate the mock-up itself in ICAT. So on that mock-up, we will create the actual bus scenario, or as per that, we will do the FAS and FDS testing. So this test we are fabricating. This is for FAS and FPS testing. This is the isometric view, and we are fabricating this. You can see on the right side, this is actual photograph of the setup. This setup is under progress. So in this setup, we can adjust the height, length, and width of the mock-up as per the actual bus sizes that manufacturer will define in their checklist. So as per that, we will do the setup before the actual testing, and this setup will be ready by November 2022. This is the 12-point checklist. This checklist criteria is mentioned. All the criteria are as per the global standards. So some criteria we will check during this mandatory testing, but for others criteria, manufacturer have to provide the IS or IS standard report as per the IS or NABL standard. So other parameters we will verify as per the documentation. This is the hydrostatic test rig. This test rig we will use for hydrostatic testing of the pipe network. So we have because this is the low pressure system, water system, low pressure system. Therefore, we have kept the hydraulic pressure of about 35 bar of this test rig. So this test rig is able to maintain the pressure of 35 bar continuously during the whole duration of the testing. So this test rig will cover all type of water mist system because all types of water mist system are low pressure type of system. So this test rig will cover. There are apart from the above mandatory testing, there are several other tests are mentioned in the standard. Those are guidelines tests. For that test, ICAT already have these facilities. So like testing sign sweep and vibration test, we have mechanical shock test. We have 6-ton ED vibration shaker. We can do vibration testing in this shaker. For testing of the high and low temperature of electronic and mechanical parts, we have climatic chamber. So we can do all high and low temperature testing in this climatic chamber. And this is salt spray test. We can do the salt spray test of electronic and mechanical part of FAS and FPS with this salt spray chamber. This is a testing facility for endurance test of high humidity of electronic parts. So we can use this humidity chamber. So all because seeing the size of this component, including mechanical part and electronic part, we have this testing facility available. We can test this humidity testing in this channel. Besides this testing, as per the AIS 135, we have another test facilities available in the CTL, which are for the bus testing. So we can see here. This is the seat testing facility for the buses. Some mandatory testing for the seats like static seat anchorage test, seat strength test, performance of head restraint, energy dissipation. All these facilities are available with the CTL. We can do the seat testing in component lab of ICAT. These are safety belt testing. It is not mandatory for buses, but it is for all M and N category. So I am included this in future if some standard is applicable for safety belt also for driver and co-driver. So we already have this safety belt testing facility available with us. So we can do the safety belt testing. Like you can see, we have emergency locking retractor and a retractor durability test rig. These are another type of 6-station retractor durability test rig and retraction and force extraction force measurement test rig. And we have SLAD facility also for dynamic testing. It is available in our another lab, PSL lab, but we are coordinating as a whole. We are coordinating for safety belt, so we can do all so that it is ease for the customer. They have to contact with only one person. So I have included the PSL part in this presentation also. This is FDSS test facility. This is already available facility in ICAT. This is as per the AIS 135 2016. So ICAT is the first who has developed this FDSS facility around the test agencies. So we have tested more than 9 to 10. We have given more than 9 to 10 certification to the manufacturer with that facility, and we are conducting another development test also for various prestigious organizations. There are some 4 scenarios for FDSS testing. This one is for high fire load scenario. This is high fire load scenario with a fan. This is a low fire load scenario. This is the reignition test scenario. This is our another facility. This is still test platform. With this facility, we can do the rollover testing as per the AIS 52 and AIS 31. So our facility has maximum the capacity of 50 ton, and the length is 20 meter and width is 3.5 meter. So with this facility, we can do the rollover testing and stability testing for all types of buses. This facility is for survival space. Actually, it is not for bus. However, it is for the truck testing. This facility is for front impact test, and the second one is for rear body strength test. This is a window retention test facility. This facility is used to test the window of the buses. We can do this testing on the mock-up or inside the passenger cabin. So its capacity is 1000 kg and displacement is 140 mm. This is window frame testing facility. We can do the window frame testing also as per the AIS 068/2005 with amendment number 1. We have bus window durability test rate, vibration shaker, salt spray chamber, corrosion, salt spray chamber for corrosion testing, ozone chamber, and oven for heat aging testings. We also have UTM for strength test, and for hardness test, that facility is also available. So we can do the complete AIS 068 testing here in ICAT. So these are the other testing facilities which will be conducted on the component test lab. This is windscreen wiping area test as per IS 15802 and interfitting testing as per AIS 047. These are the facilities, upcoming testing facilities which we are planning in ICAT. This is a relevant facility, FAS and FDS test facility as per the AIS 135. So this will be very soon. We will be installed in the component test lab, and we are hopeful that by November we will be able to conduct the testing for the manufacturer. And another facilities are light transmission meter, UV cut and IR cut for advanced safety glazing material, electric vacuum pump durability test rig, performance test rig of electric compressor, light source projector, 2 numbers for sheet and float glass testing, high capacity radial fatigue test rig for wheel rims. Actually, this facility is already available, but we are upgrading the capacity up to 150 kN or 15 tons. So this will be duly added to the CTL department. So another is cornering fatigue test rigs for wheel rim of 50 kilonewton meter. So these are our upcoming facilities. You can take the benefit of these facilities from the ICAT. Thank you. A very thank you to all of the participants who has patiently listening my presentation. Thank you. Thank you.
Thank you so much for the in-depth presentation, sir. We have received few questions and we will revert to all those questions over email. Thank you for your patience. So we are at the end of today's webinar. I once again thank all the speakers and delegates for actively participating in the webinar today. I hope knowledge shared by speakers during the technical session will be useful for the development in the field of FAS and FDS. We will share a feedback form with all of you. Your feedback will help us to improve in the future. So I, Devyani, on behalf of ICAT, say goodbye to all of you. Have a nice day. Stay healthy. Stay safe. Thank you.